Hello, welcome to my talk. I will talk about prospecting the precision of massive black hole spectroscopy with LISA. This was a work that was published not so long ago in PRD. You also find an archived version. This was done in collaboration with Enrico Barause, Shweta Bhagwat and Paolo Pani. I am Constantino Pacilio. I am a postdoc at Sapienza University of Rome. First, let me advertise that since this pre-recorded talk are short, we split the talk into two separate talks, but they are complementary. So there is a complementary talk which will be given by Shweta Bhagwat, and it's also in a pre-recorded version. First let me start with very general recap of what you can do using black hole ringdowns when you want to test GR. Well, as you know very well, black hole ringdown is the final part of a binary black hole waveform. The waveform that originates from a distorted black hole, and it can be described as a superimposition of quasi-normal modes. And if you are at intermediate times after the peak of the waveform, or if you want after the merger of the two black holes, this is a good description. Now the point is, if GR is the correct theory of gravity, the quasi-normal mode spectrum, it depends just on two parameters, which are the final mass and the final spin of the remnant black hole. And this is at the core of what allows to test GR with black hole ringdowns. There is a very general framework called black hole spectroscopy, and there are many versions, many proposals on how to implement black hole spectroscopy. Like, for example, you can implement into these three steps in which you use the dominant frequency and the dominant damping time to invert for mass and spin. Then you use this mass and spin to infer the other quasi-normal mode quantities, and then you check that what you inferred and what you measured are in agreement. And in any case, whatever implementation you like, you find that you have to measure at least three frequencies and or damping times in order to perform successfully black hole spectroscopy. And then in this paper we highlight with respect to LISA what is the impact of the precision of your black hole spectroscopy, meaning that you will measure frequencies and damping time with certain relative precision. You can define a collective measure of this precision called measurability, and what is the impact of measurability on your ability to perform black hole spectroscopy. You can see from these two plots here on the right, the upper plot shows a signal with SNR 10 and measurability 20%. And you see that uncertainties are large enough that not only you can accommodate the injected value for the mass and the spin, but you can accommodate many more. While if you just let measurability to decrease by one order of magnitude, which means that the SNR increases by one order of magnitude, you see that you restrict a lot the number of available configurations that are compatible with your signal, and in this way you put more stringent constraints on the fact that this waveform originates from a black hole which is well described by general relativity. Now, when you are with LISA, like you would like to do black hole spectroscopy and you have to resort on massive black holes. However, in order to do prospects of how much you can do black hole spectroscopy with LISA, you must have a model of population for this MBH. And the problem is the MBH population is presently uncertain. And so there are two key questions, mainly like how many events will LISA see and with which precision the quasi-normal modes can be constrained, which translates into which SNR do they have. And both answers to these questions, they depend on how the population is structured. So in the absence of a single model of population, what we do, we use a family of population models, and they track the evolution of MBH in the galactic hosts and the formation of MBH binaries. This is described, for example, in this review paper by Barause and Lapi, in order to prospect uncertainties over frequencies and damping times. We use a numerical code based on the Fisher approach in Berti and others back from 2005. And as far as which modes we include the dominant 2-0 mode and 3 subdominant modes. First of all, these populations come into two groups. There is one group which assumes as initial condition heavy seeds, which results into heavier final black holes. And then you have a second group which assumes that you have as initial condition light seeds, and this results into lighter black holes. And then if you look at the mass spectrum here of the final black holes, we color it in warm colors the heavy seeds populations, and in cold colors the light seeds populations. Well, you see that only in the heavy seed case you have final masses in the detector frame that can generate signals that are detectable by LISA appreciably. And the reason is, if you translate these masses into what is the dominant ringing frequency of the ring down, you see that warm colors, heavy seeds, they ring into the like millihertz or centihertz, while cold colors, light seeds, they ring at the hertz or tens of hertz, so they are mainly outside the LISA band. So this is the first thing. So if we are in the heavy seed scenario, we have a good chance of doing black hole spectroscopy with LISA, probably. But then you have to look at how many events you will be able to detect and with which SNR. And for example, here on the left, there is the intrinsic rate of binary black hole events, which also includes the events that you will never be able to detect. And you see that depending on the subpopulation of heavy seeds, there is a large variation. You can be into cases in which you have like 2 or 6 events per year, and then cases in which you have 300s. These labels correspond to the different hypotheses that underlie the different population models that comprise this group of hypothetical MBH populations. Okay, but then how many events you will detect and with which SNR? And you see here that, of course, I mean, if you are in the cold case, light seeds, you will not detect basically any event at a substantial SNR. While if you are in a warm case, in a warm color case like heavy seeds, you see that there are cases here, the one that we label as delays, and most of these events will be detected with a very high SNR of order 1000, but there are not many. I mean, they are 2 or 6 or 7, so you will have very few events with very large SNR. In the other case, the ones that we label as short delays, you will have many events, but SNR is widespread. So only a tiny fraction of them will ring at very high SNR. So now, this fact results into a fact which is displayed into this plot, which is the measurability of events per year. And you see that basically you will never measure per year events that have measurability at sub% level. And the reason, of course, is that you have only few events with SNR 1000s in one case, or in another case you have many events but only few of them have SNR 1000. So this basically will never be possible with individual detections. With individual detections, you see that you can do spectroscopy with at the percent level with basically all the populations that bracket the uncertainties over the heavy seed hypothesis. However, if you are in the case that we label as short delays, you see that you have enough events to stack. So basically, if you stack enough events, you can end up by putting constraints at sub-percent level by stacking events at the percent level, but this is only the most favorable cases. In the most unfavorable cases, you will not have enough events to stack anything, and so you will be basically you will meet a limit on the precision with which you can do black hole spectroscopy with LISA, which is the percent. But even by stacking, you cannot go below sub-percent. Okay, so this is one of our main results. And let me go to the conclusions of my part of the talk. So conclusions: if you want to do massive black hole spectroscopy with LISA, you have the potential to do tests at the 1% level of measurability for individual events and sub-percent if you stack events in the most favorable cases, the short delays cases, while in the least favorable cases you will not have enough events to stack, and so you will be blocked at the 1% level. But what about light seeds? I mean, we only discussed heavy seeds because these are the ones that can be detected by LISA. With light seeds, okay, you cannot use LISA, but you see that if you have a detector that operates at the decihertz level, basically you can use a decihertz detector, like for example this IGO that has been proposed to operate in the future, or a fraction of them, the ones that ring at, I don't know, like at 10 Hertz, for example, they can be also detected. They could be also detected by Einstein telescope. Now, the final remark that I want to make is that you don't have to assume that only one of these two groups will exist. I mean, they most probably will coexist. You will have at the same time a fraction of MBH population that comes from heavy seeds and a fraction of them that comes from light seeds. So these two situations are not mutually exclusive. So what we said about LISA is fairly robust, but also there is another subpopulation that probably deserves more studies from the perspective of other detectors. In our paper, we also have prospects of doing MBH spectroscopy with Einstein telescope, but probably the scenario of doing MBH spectroscopy with a decihertz detector deserves more attention. That's it, and thank you for listening. And yes, and don't remember to listen also to Shweta's talk, which is a companion to my talk. Thank you very much, and enjoy the rest of the talks and the rest of the conference.